Here we are in section 2.3 where we're going to finally get to the punchline of this whole section. We're going to talk about the derivative. Fantastic. That's exciting. So, the very first thing we should start off doing is talk about the formal definition of the derivative, and then we'll go ahead and show what that looks like and go to the different notations and make sure we really get what's going on. But to start off with the formal definition, I want you to understand that what we're really talking about is a limit. And it's going to look like this. It's if you take a second and pause and don't let all the letters and everything kind of scare you, what you'll recognize for our formal definition of limit is its slope formula. Notice, because when we say, like, if I were to say to you, f of x equals 2, well, what we'd be saying is the y value, that's the same thing as y equals 2, right? So here what we're saying down here is we want to evaluate our function at some y value evaluated at a number minus another y value at a different number over, and then you'll notice down here, if you kind of break it up like this to make it fit into slope, you notice there's just our one value that we were looking at right inside, because here we had x plus h, and then over here, kind of think of that as b and b. So if you notice, what we're really just talking about here is that's just your slope formula, y2 minus y1 over x2 minus x1. There you go. All right, so the formal definition of the derivative is just really, it's a fancy way of writing slope. Now, we can simplify this denominator just a tiny bit. Let me actually, I'll leave them there. So when we go ahead and simplify this denominator, you'll notice, all right, the numerator we can't touch. We can't do anything in the numerator because it's all saying evaluate your function at x plus h and then evaluate your function at x. So yeah, we can't simplify there. But down here in the denominator, what we really have is x plus h minus x. And combining like terms shows us, hey, those subtract to 0. So our denominator, we would just be left with the limit as h approaches 0 of f of x plus h minus f of x divided by h. So this is a simplified version of it, and usually, I don't want to say usually, but a lot of books and a lot of teachers will just jump to that being your formal definition of a derivative. But I do want you to know where it came from, that it's just slope. So if you ever forget, or if you ever want to think about it logically, you say it's just slope. So it's y2 minus y1 over x2 minus x1. Boom, there you go. So now we can go over here and you'll see there's a little picture kind of describing what that h meant. What we're saying, if you think about it, since it was, I'll zoom out so I can get both things. Since it was x plus h for one of the values, and then for one of the x values, and then x for the other one, what we're saying is it's just a distance between one x value and the next. So here what we're saying is I have some distance from x to x plus h, and that distance would be h because that's how much you changed. So that's what this is showing. Is the idea here is we have a secant line. If you kind of imagine starting at one point and then you see the red point up here, and then that would be the slope of the secant line. And then the derivative is saying is let h approach 0. So what would that mean? What would that mean? Because remember, when we talk about limits, we're not talking about when it actually reaches that value. It's just as it gets really, really close. So as h approaches 0 means that this red dot is sliding in closer and closer and closer and closer and closer until eventually that it's basically on top of each other. So to help you visualize this, if you go into your section 2.3 where you found this video, you will notice in the same area there is a link here. I would like you to click on that link, and this is just if you want to do this in a second and you watch me do it the first time, you can. This is just a link that will let us physically touch and see how this feels. So the first thing I'm going to do is change the equation just to x squared so it matches what we have on our page, and I'm going to slide my secant point over just so it kind of matches what we had on the page, and you can see the idea here. And note, for view, if you would like, there's these little buttons here in the corner where you can zoom in and you can move left and right to kind of reposition So if you, just to make it view however you want it to view, you can do that. So you see here we have our two dots for the secant line, and then I have a dot for the tangent line. So if I go ahead and move my tangent line dot so it's on top of my bottom secant dot, you can see the red tangent line is nowhere near the blue secant line, but that's because the dots for the secant line are very, very far away. So now as I move my dots closer together, as my secant line dots get closer and closer together, you can see the dotted line is approaching the tangent line. It's approaching. So now as the dots get very, very close together, what do we notice? Now they're not exact, so you'll notice it's not exactly on, but what do you notice about this? Well, we can see that the tangent line is basically the secant line when the dots are very close together. And you can have a lot of fun trying to zoom in as much as you can possibly zoom in. You'll see, and as we get closer in, you can see that the dots are not actually all lining up, which is why we didn't have a perfect fit, because it wasn't perfect. So what I can do here is kind of, all right, move the tangent line, get these dots even closer together. So there's really as little space between them as I can, then get the tangent line on as close as I can get it. And you can see it fits better. And if you want, you can zoom in some more. Okay, I'm not going to keep doing this. I think you guys get the idea. So what is the statement we're trying to make? What's the big idea? Well, let me see if I can reset this graph by cheating. Voila. There we go. So what's the statement we're trying to make? Well, the idea here is as the distance between dot A and dot B, as h approaches 0, what we're actually calculating is no longer a secant line. What we're actually calculating is a tangent line. And remember, a tangent line means it crosses our graph at exactly 1 point. So what we can say is that this formula here gives us, instead of the slope of the secant line, when h is approaching 0, it actually gives us the slope of the tangent line. Okay, really, really important idea, because if secant line was average rate of change, because you had a distance, you had from 1 second to 2 seconds or something like that, the tangent line would no longer describe average rate of change because it's at one individual point. So therefore the slope of the tangent line would be your instantaneous rate of change. So that's kind of the cool thing now. So the formal definition of derivative, we can really see why it's talking about instantaneous rate of change, and it's because it's describing the slope of a tangent line, because the distance between the 2 points is 0, or basically 0. So now we're going to have a couple notations to talk about derivatives. These two notations, I want to say, are interchangeable. So I argue some of them are better in different contexts, but you have to be familiar with both of them. The first notation for a derivative is dy dx, and you can think of it just like you would like slope. Remember, you probably saw this in a previous class, change in y over change in x, because that's what slope meant. So you'll notice here it's very similar notation. Just instead of being the average rate of change, which is what these deltas meant, we are now talking about instantaneous rate of change. So we change it from the Greek letter D to the whatever it would be, Roman numeral, or not Roman, but the I don't know, the American. It's not the American, the English alphabet. Anyway, whatever it is, we're changing it to the English alphabet, letter D, and that will actually change when you get to Math 218. We're gonna have another D that we have to use there. So anyway, so you can see it's just the same idea as slope, because that's where this formula comes from. So derivative dy dx. Or sometimes you might want to, you'll start with a function like f of x and you're going to take the derivative of it. So what we do to notate that we took the derivative is we put a little prime on it. And therefore now those are your two main notations for derivative. You can either put a prime or dy dx. Okay, and a prime just looks like a little apostrophe. Okay, so what does a derivative look like in notation? That's what we just did up here. What does it look like on the graph? Well, I already mentioned it to you. What did the derivative look like? It is the slope of the tangent line. Okay, so what does average rate of change look like? Well, that was slope of the secant line. So a derivative, keyword derivative, is the slope of the tangent line. Okay, so let's take a quick read here, and we're not going to actually calculate any derivatives right now. All we're going to do is see if we can take a context and make some meaning out of it. All right, so let d of t represent the distance a car has traveled on its trip to Las Vegas, where d is measured in miles and t is measured in hours. Describe the meaning of each of the following values. So what we have to remember here for derivative notation, that is really, and this is where I always like to change it to the other notation. I like to remember that this is really change in distance over change in time. It's slope. So think about your units. So we can put this like slope. Distance was measured in miles and time was measured in, actually I'll write it as a fraction. Time was measured in hours. So now it's a little easier to see. Our derivative here is measured in miles per hour. So if we're talking about the distance the car has traveled on its trip to Las Vegas, what are we saying if it's going negative 20 miles per hour? Well, that's kind of one of the fun things here. We can actually put meaning to derivatives if it was given in the problem. So here what I would say is if we're talking about a car traveling towards Las Vegas, negative would mean it's traveling away. So what I might put here is the car is traveling at a speed of 20 miles per hour away from Vegas. Now notice what I did not put in that sentence. I didn't put in a negative 20, did I? I just put in 20. Why is that? Well, because the negative has contextual meaning if you're traveling towards or traveling away. So here, because I put away, now everybody knows, oh, it was negative. So if you had put a negative in the sentence, then you would almost have a double negative in here. If it was a traveling at a speed of negative 20 miles per hour away, then that would mean you're actually moving towards Las Vegas. So just watch for that in word problems. A lot of times when we're doing them, especially in MathAS or systems like that, because they'll have a description in the answer where you're typing in your answer, they're going to say, what speed were you moving away from Las Vegas? Then you just type in 20 miles per hour. So just watch for that. Okay, so depending on your comfort level, you may want to try pausing and writing out the next one, or you may want to try just keep watching. So pause the video. Okay, here we go. So how do you describe this one? Well, it's very similar. But instead of traveling away, since this is a positive value, and watch our notation, notice that it has the prime on it, which means it's a derivative. So it's again, so I would recommend rewriting it in the change in output over change in input. So this one would be 68 miles per 1 hour. So therefore we could describe that as, again, we are traveling at a speed of 68 miles per hour toward Vegas. Okay, I hope this is making sense. So now, the next problem, this one's a kind of a brain, makes your brain hurt a little bit. So I want you to stop and think about what it's saying. Okay, and then, so pause the video, take a thought. Okay, so now, hopefully you thought about it. And what it's saying is, does it make sense? Can you have a speed of 0? Well, absolutely. Maybe you're at a stoplight, or maybe you stop for lunch, or something like that. But the idea here is, oh, and then please note, there's also a time. So we can include that in the meaning as well. So what I'm going to say here is something like after 3 hours, we are stopped. Maybe you actually reached Vegas and you're there, so why would you drive anymore? Okay. So hopefully that makes sense. So now, could problem number 4 coexist with problem number 3? Or do these things contradict each other? So take a look, pause your video, Okay, so now the idea here. Notice, if you have to watch very carefully, and this is why the primes can be a little misleading, is there's no prime there. We're not talking about a derivative. I'm just talking about the basic function. So therefore, what we're saying here is it's not a speed. This is just like a MAT212 function. I put in a time, I get out a distance. So therefore, after traveling 3 hours, after 3 hours, we're not going at a speed. We are 184 miles. And then I guess I forgot how this was defined. I would say we are 184 miles on our trip. We've gone 184 miles. So let me rephrase that. I'll say we have gone 184 miles toward Vegas, something like that. So do you notice how you can have the input of 3, which both means 3 hours, just how you interpret your answer is different. Because if it's a derivative, it's a rate of change. It's a slope of the tangent line, which has a slope of 0, which means we're not moving. Where here, this is just talking about our position because it was a distance. Okay, so the next several, I'm going to go ahead and just fill these in. You go ahead and try them on your own and see if you can get them. Okay, so on these last 3, number 5, 6, and 7. So number 5, hopefully you interpreted this something like you first noticed there's no prime, so it's not a derivative. So therefore it's just a time and a distance. So at time 0, that's when we're starting our trip. We haven't traveled at all. So maybe you said something like, at the start of our trip, we have traveled 0 miles. Perfect. And then since this one has a prime, now we're talking about a rate of change. Now we're talking about our speed. So therefore, at the start of our trip, we are going 15 miles per hour. Perfect. Now, number 7. Number 7's interesting because it's actually saying the exact same thing as number 6. It's the exact same interpretation. It's just the other notation. So remember, I wanted you to be adept at using both versions of derivative notation. So I just wanted to show you one there. And I wanted to point out, this is how you say we're putting in a value. So the input is 0. So it's the exact same notation as here. When we put in 0, we get out 15, and here's our derivative. Okay, hope that makes sense. So now, let's go to another kind of representation. All right, so if we had something like this, where we have a rocket that we're launching, and we're saying, given the graph to the right, and note there's time and r. So given the graph to the right, if the horizontal axis represents time in seconds, and the vertical axis represents the height of the rocket in feet, answer the following question. All right, so let's see. And note that the units on the graph are counting by ones. So it's 1 second, 2 seconds, 3 seconds, so on. Okay, at what time was the rocket traveling the fastest? Okay, so if this again is measured in time, let me label these. So time was measured in seconds, and this was measured in feet. How on earth would we get to talk about speed? Well, speed is a measurement of miles per hour or feet per second or something like that. So we need to get one thing divided by the other. Well, hey, isn't that what we were just doing with derivatives? So if you think about kind of like making a secant line, even though we're not going to want to do a secant line, if you made a secant line, think about your units. The slope would be change in y over change in x, or in this case, it would be change in r over change in t, which has the units of change in feet over change in seconds. So we have feet per second. Perfect. So, but we don't want an average rate of change. We want the exact time. At what time is it going the fastest? So what we need to look for is, where does this graph have the steepest slope? If we were to draw a tangent line, at any point, okay, so we'd have a slope. Let me zoom in, make it even more obvious on your screen. A slope there, where if I test this point, something like that. So clearly the green line is steeper than the blue line. So let's keep trying here. So if going to the right, it looks like it's just going to keep getting less and less steep. So let's go the other way. Let's go to the left. Here, this red dot that I just drew clearly has a steeper slope than the green. So I think we're all coming to the conclusion, because of the way this graph is shaped, the steepest slope was at the beginning. So what I would say is, at what time is the rocket traveling the fastest? I would say at launch, or um, at 0 seconds. So the instant it is launched from the launcher, that's when it's going the fastest. Then after that, it seems like it's slowing down and slowing down, which makes sense. Throw your pencil up in the air and watch what it does. When you throw it up in the air, it's traveling fast and it's slowing down and slowing down until eventually it starts coming back down towards you. Okay, so at what time is the rocket traveling the slowest? So instead of looking for the steepest line, we're looking for the yep, you got it. The not steepest line, the shallowest line, which again looks like it would be right here at the end. So let's figure out what time that is. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 seconds, as long as I counted right. So to me, that looks like at 11 seconds. Now, here comes the hard part. Approximately how fast is the rocket traveling at 3 seconds? Okay, so now we're going to have to start putting stuff together, what we learned about the derivative and what it means and how we find it. So let's really see if we can put this all together. So at 3 seconds, there's 1, there's 2, there's 3. So right there, how fast is the rocket traveling right there? How are we going to figure this out? Now, this is going to be interesting because how do you find the slope of a line if there's no line? Well, let's draw a line. We're going to have to do that. So what we'll do, let's see if I can do this not with pink. All right, highlighter, that didn't quite go as planned, but yeah, that's not going to go. I'm just going to do it by hand and we can all laugh at how horrible my drawing is. Okay, so drawing the tangent line, and this is what you're going to have to do anyway for yourself. So there you go. There's my tangent line. Now, how am I going to figure out its slope? Well, I know 1 point already. 1 point on this line is 3, 2. So how do you find the slope of any line? Well, you look for 2 points. So what we're going to do is try to find another point that's easy to read. I would say this one looks pretty good right there. That one to me looks like it was 1, 1. So now, how we're going to find the slope of this line is by using our slope formula. The slope would be, all right, y2 minus y1 over x2 minus x1. So let's see, what is that going to be? That looks like it's going to be, try again, not 2, 1 over 2. So it looks like it's about 1/2. So what does that mean? Well, again, think about your units. Think about our slope. The top, the numerator, had the units of feet. The denominator had second. So we're traveling at 1 foot per 2. That is the world's worst second. There we go. We're traveling at about 1 feet per 2 seconds. Or you could rewrite it as a decimal and say it's a half a foot or 0.5 feet per second. Anything like that is acceptable. But there's something very important I want you to realize here. How accurate is our number? I would say it's kind of bad because we just kind of free-handed a line and kind of figured it out. So here's what I'm going to say. When you're doing these problems in Math AS and you're doing these problems, please, please, please print out the graph so you can get a good sketch. It's very hard to draw this on your computer monitor, especially if you don't have a pen like I do. So please draw it out, get a good line, and get approximate points. Math AS does have an error tolerance built into it, so if you're close, you'll get marked right. It's not looking for an exact answer. But if you're having a really hard time, don't spend a lot of time trying to figure this out. If you think you're doing the right thing, just send me a picture of your work, send me what's going on, and I will be glad just to tell you the answer they're looking for, as long as you're doing it right so you can get your credit. Okay? All right, so now, let's keep going. Problem number 11. It looks as if the graph will have a horizontal tangent at 11 seconds. What would that mean in context? So thinking about what's the meaning of that line? All right, so if we do this, if it has a horizontal tangent, excuse me, I'm going to cough. Excuse me. A horizontal tangent. What does that mean? Well, what's the slope of a tangent line? Slope is 0. So again, what does that mean? Okay, so since we're going to talk about meaning, let's put our units on it. Remember, this is a slope, so it's a rate of change. So it's change in y over change in x. So again, it is feet per second. So what would that mean? Well, if it has a slope of 0 feet per second, it means it's not going up, it's not going down, the speed is not moving. Um, because remember, it measures the height of the rocket. So it might be moving left and right. It might be flying over towards something, but it's not going up nor is it going down. It's just reached a peak height. So what we could say is the rocket has reached well, if it's going up, that would maybe be like a maximum. That's the world's worst A. It's maximum height. Okay? So then what would you predict happens next? And then this is up to you. There's all sorts of different answers. So let's take a minute, think about it, think about what you'd predict. Most people, okay, predict that it's going to go down. But some other students think that have interpreted as it exploded, it hit something, and that's why the line stopped there. So I buy any kind of answer you want to put there. All I'm asking for is thought. Okay, so now let's just practice drawing derivative graphs. So if these are position graphs, I want you to think about what the derivative graph would look like. Okay, so what does a derivative mean? The derivative is the slope of the tangent line. Now, when we draw derivative graphs, let me even make this a little better. Instead of the word draw, I'm going to use the word sketch. I do not want accuracy. I really don't care. All I really want you thinking about is positives and negatives and zeros. Okay, so let's think about this. For the first graph, I'll do this first one with you. When we start here, if you look at all these values over here, it looks like our slopes are all positive slopes. Does that make sense? And then it looks like they're getting less and less steep until we reach some maximum right here at 1. It kind of looks like we'd have a horizontal tangent line there. And then our graphs are going to start to have negative slopes. Does everybody buy that? So to draw the derivative graph, what we're going to do is say we started off positive. And then our values got lower and lower and lower. They still were positive. They still had positive y values, but they eventually reached 0 at 1. So our graph is going to do something like that. We're going to start with positive values and then reach 0. Now, you might say it looks something more like that. I don't care. As long as they start in the positive values and then reach 0 at 1. Then after 1, notice we have negative values, negative values, negative values, negative values, and we have negative values all the way until we reach another 0 right here. So what I'm going to do is put another 0 right here, and we're going to connect the dots. We're going to say our slopes went negative, and then they turned back around, and they still were negative. They were all negative slopes. They're all decreasing. But do you notice they were shallow negative line, shallow negative line? Here, I'll highlight as I go. Shallow negative line, a little steeper, little steeper, little steeper. And then at some point what happened? They stopped getting steeper and they started getting less shallow. So you see we got more negative, more negative, more negative, more negative, and then at some point we started getting less negative, less negative, less negative until we got back to 0. Then after that point we're back to positive slopes. So it would look something like that. There is our derivative graph. And how would I notate that? Well, instead of calling it f of x, we're going to call it f prime of x. There we go. Now we've got a derivative graph. Okay, so now I want you to pause the video and try to do it with the next one. Okay, and I'm going to fill it in. I'm going to pause the video as well. Okay, so here is my derivative graph that I just created. This one I called g prime of x. Okay, so let me walk you through my thought process. So the idea here is I noticed that the graph started off, well, the first thing I did actually is I first looked for all my horizontal tangent lines and immediately put zeros that I knew I had to go through. And then I just said to myself, where did I start? Well, I started over on this side, I started with negative slopes. They're all going down. My graph was going down, so therefore I had negative slopes. And I still had negative slopes all the way to my first 0. Then after that, we had positive slopes. So I made sure all my values were in the y-axis, above the x-axis. Then after that, we went back to negative slopes until we hit 0, and then positive slopes from there on out. So there you go. That's all I'm looking for when we are drawing derivative graphs. That's all I'm looking for. And a lot of times what we're going to have you do is match them. So you're going to have to you're going to have a couple graphs and they're going to say, here are two graphs, pick which one is the f of x and pick which one's the f prime of x. And you're going to have to look for qualities where you can argue that which one's the derivative, which one's the original. So make sure you practice those types of problems. So to recap, what was the big ideas? What was the objectives for this lesson? Okay, so take a second, pause, reflect, pause your video, and then here we go. Okay, so what were our big objectives? We learned the formal definition of the derivative. Okay, that was the slope formula with the f of x plus h minus f of x. We haven't done much with it, but we're going to do that in the next section. We're going to do some work with that. So we learned the formal definition of the derivative. Just make sure you're understanding a derivative is slope. It's just the slope where the points are so close together, it's no longer a secant line, it is a tangent line. So we have learned notation for the derivative. That's incredibly important. Okay, so make sure you've got that. Wow, and it helps if you actually spell the word derivative. There we go. Okay, notation for the derivative. Make sure you know both of them. There are two different types. You have the prime notation and you have the d notation for the change. Okay, the other very big thing that I kind of hammered a lot is meaning. Make sure you've got the meaning of a derivative, that it's a rate of change, because it's just a slope. Change in y over change in x. That's all we're doing. Okay. And what does a derivative look like on a graph? It is the slope of the tangent line. That's right. Okay, so those are the big takeaways from this section. All right, happy studying.